So I don't see the outline.
Which outline?
Can you see the screen with gravity?
Yeah.
Gravity. Can you see my mouse move?
Yeah, it says gravity tempers singularities.
Okay, okay, good. All right, that's what I want there. All right, so let's see. So experimentally, what we've got is that the supernovas, observations of supernovas about 20 years ago, a little more than that, by Silk and others, indicated that or showed that the that the expansion of the universe was accelerating. And observations of the CMB by the Planck satellite and so forth indicate that the acceleration began about 4 billion years ago when the universe was about 10 billion, when our pocket universe or whatever, the known universe, let us say, was about 10 billion years old, or 10 billion years since the time of infinite temperature, which is Weinberg's expression. So that's the basic experimental situation. And the natural, there are various explanations. One is that simply that when you look at general relativity, let me see if I can get the right. Well, let's see, I need to go to a different screen, presumably, to find, oh, we're in that screen. What is this? No, that's not right either. I'm just trying to find the part of my book that discusses such things. Yeah, there it is. So if I grab this book thing and put it up there, then I can grab that and right, go here. So the basic thing is that so Einstein's equations are based on this action here. Now, if you just add to that a constant lambda, let me see if I can connect my iPad to this. And so I guess I can go back here. And I think I want to get rid of this. Oh, there, that's what I do. So this is 28 Feb.
All right, do you mean to be recording, Professor? Oh, wait. Okay, I see the recording.
Yeah, I started recording and I thought that would be a good idea.
Yeah, I didn't get a notification saying you were. That's why I thought you might have forgotten.
Yeah. So, what we've got here is that S is, oh, let me bring this equation over here. So the so this is Einstein's action. So we've got C cubed over 16 pi big G, and then an integral. And if we do simply R plus lambda, where lambda is a constant, square root of G d fourth x. So that's this thing here then is called, this thing is called a cosmological constant.
Where is it? Are you drawing on the?
Oh shit! Yeah, thank you. I need to get this going under QuickTime, assuming that QuickTime is going to work for me. File, new movie recording, iPad. There we are. Right.
Oh, okay.
So this is called the cosmological constant. And way back when Einstein invented general relativity, he included lambda because obviously a constant is even simpler than, well, is simpler than this expression here, which of course involves lots of derivatives and indices and so forth, and second derivatives of the metric G mu nu or GIK. I try to avoid Greek letters because we don't speak Greek. So he originally included lambda, and he also he thought that maybe the universe was static, and so we worked out a static solution. But then I guess, I don't know the history that well, but he then dropped the cosmological constant. And the reason he dropped it was that, I think the reason he dropped it was that by then Hubble's observation indicated the universe was expanding. And so he dropped the cosmological constant. That's my memory of the history, but as you know, I'm not an historian in any sense.
So are R and lambda, are those just are those matrices? Are those
Oh, all right.
scalars?
No. They're functions. R is the Riemann scalar that we talked about earlier. Let's see if I can grab okay, curvature. So when you analyze curvature of a manifold, you find that it's related to these Christoffel symbols, which unfortunately are written as capital Greek gammas. We really need a better notation for that, but people are so rigid in their adherence to conventions that I don't know how to do that. Anyway, remember that gamma is just, so let me just review for you what gamma is. Gamma is here, if you imagine that our space-time is embedded in the higher dimensional space-time, and that the basis vectors in that space-time are called E sub n, E sub I, and so forth. And if you also say that you can take the dot product of two of those basis vectors in the higher dimensional space, let's say it's 5 or 6 dimensional, then this zeta, it's like eta in that it has just minus ones and plus ones and is diagonal. And so in other words, if the embedding space is all space, then it's just a diagonal matrix of 5 dimensions or 6 dimensions. If on the other hand, it's a space-time, it could have 1 time dimension, two time dimensions, 3, and then it would have 2, 1, 2, or 3 minus signs on the diagonal of zeta. Anyway, that's how you make the dot product of these basis vectors. And then the derivatives of the basis vectors are covariant second rank tenses. These guys are covariant vectors because they were originally defined in terms of the points on the manifold. So the points on the manifold are these are physical points, and so they are, God, you must be going dizzy as I run past this. So the points on the manifold are physical and independent of the coordinates, like this. Or in fact, let's even go, well, I guess that's as far as we can go backwards. So the same point P is represented as P prime of X prime or P of X prime or P of X. It's independent of the coordinate system because it's a physical point on the manifold. But if you then ask, how does that point change when you change your coordinates? Well, that's the basis vector. And P is a point in this higher dimensional space time. And so this derivative is a vector in this higher dimensional space time. And because the point is physical, you get that E prime I of X prime, which is this derivative, is the same thing as this derivative. And then ordinary calculus tells you that's this. And so you get this rule here. So when we change our coordinate system, the basis vectors transform as covariant vectors. And a change in the point on the manifold is the basis vectors times the change in our coordinates, and then you just sum over I. And then the dot product of two basis vectors gives you the metric of space-time. So that's, I think that's the simplest way of looking at this. In many books, they don't do that. Instead, they pretend that a higher dimensional embedding is irrelevant, and so instead they force students to somehow just imagine what the metric is. I don't know.
Well, does curvature only make sense if our space-time is embedded in a higher space-time?
That's my view.
Okay.
I think that's in fact true. So the metric then is the dot product of two basis vectors. So you have a sum like this, where this zeta is some diagonal matrix. Anyhow, once you've got that, then you take the dot product of a basis vector with the derivative of a basis vector, and that gives you this Christoffel symbol. And then when you work out the curvature, so this thing always keeps popping up. You work out the curvature in this way. This is all in the book. I hope you have a copy of the book.
I do.
Yeah, so you should be able to see this in the book. You basically just imagine then that you've got this curved surface, and you go around the curved surface. It doesn't matter which way you go, but as you go around it, you parallel transport this vector around it. Parallel transport, by the way, was explained back here. And in fact, I really need a good figure for parallel transport. Let me just show you what the basic example of parallel transport is. So there's say here's the North Pole, and there's 0 degree longitude, there's 90 degree longitude, And so you imagine you take a vector here, and what I did was I started a vector in the y direction. So let's switch colors here to blue. So we've got a vector here that points in the y direction, and we transport it, keeping it, not changing its direction relative to the tangent plane. So in other words, we have a tangent plane here, and then another tangent plane. As if we go up this curved surface, we have you get different tangent planes. And so when you keep the vector with constant angles relative to that tangent plane, and then you rotate the tangent plane, the vector rotates to some extent. In any event, it's, oh, I didn't mean to go to blue. So eventually this thing, when it gets up here, it's pointing in the minus theta direction. And so when you transport down here, it goes like this. And when you get to the equator, it's just pointing in the minus z direction. And so then when you transport it around, again, parallel transporting it around on the equator, nothing much happens. But when you get to the origin here, you find that something that was pointing in the plus y direction is now pointing in the minus z direction. And that's a measure of the curvature of the sphere. And to do this, to figure out, I'm trying to get this to go away. So to see what this is analytically, what you do is you go to a small square, as opposed to here I did a huge triangle. And then you go through this argument here, a lot of indices. I think you just have to sort of work through it. But so you parallel transport the this vector v along around a square, and when you do that, you see what. Let me get rid of this. It keeps coming back. It just keeps coming back. So the equation for parallel transport is that the change in the vector is basically just this sum of Christoffel symbols on the vector coordinates, and then a sum on L and the dxLs. And that's how the vector then changes as you go from there to there. And then you do the same thing this way, and then that way, and then this way. And when you finally finish up, the total change in that is given by this. And this factor here is just the area times a plus or minus 1. And so the curvature then is the rest of this. And it then turns out to have these various minus signs, and its derivatives of the Christoffel symbols, and then a quadratic form in the Christoffel symbols. And this is called Riemann's curvature tensor. So this is the curvature. And then if you sum over it, it has various symmetries. If you sum over it, where am I summing? Here, you sum over it, you get what's called the Ritchie tensor. So you sum on K here. Whenever you have a repeated index in GR, one up and one down, you sum over it from 0 to 3. And then then you're left with something with 2 indexes or 2 indices. You then sum over those 2 in this way, which is equivalent. That's equivalent, of course, to R is equivalent to RII. Anyway, you sum over that.
Oh, okay.
In fact, you sum over I and n, and you get a scalar. And that scalar is the thing that occurs in the Einstein action, which is proportional to an integral of r, and then square root of the metric, square root of the absolute value of the determinant of the metric, d4th x. So this absolute value of the determinant metric, this thing is a scalar. That's why you have this square root of g everywhere. Everywhere you have a d4th x, you have the square root of g, and that's just, it's basically a Jacobian. And so the original idea was, and it's still a live possibility, is that this thing is r plus lambda square root of g d4th x. My g here is absolute value of the determinant of GIK. And then you take the square root. Anyway, so that's one possible. So dark energy could be, lambda could be dark energy. Dark energy is a name that one of our recent colloquium speakers, Michael Turner, gave for this excess energy density, about which we have no idea. Well, I mean, we don't know what it is. We have plenty of ideas, but they could well be absolutely all wrong. Now, there's a nice wiki page on this, and one of the possibilities here is that there's a scalar field or several scalar fields, and if you compute the pressure, you get this. You compute the energy density, you get that, and you take the ratio, and this then determines what the field behaves like, and that's discussed here in let's see, where did I? Yeah, all right, density and pressure. Right. So the idea here is that this W is P over rho, pressure over density, quite generally, and it's P over c squared rho, c of course being the speed of light. So this in general is the energy density of a particular component. And of course, what one should do is one should sum over all the possible components, because there can be many different, I mean, if there's anything to this explanation of dark energy, which goes under the name, by the way, quintessence. I think this was first, well, the basic ideas here were first introduced by Peebles and then by Steinhardt. I think he used the term quintessence. And then also Carroll, who wrote a rather nice book about general relativity. So let's see. So you see, that's the same thing here. You take the energy, this basically is the Lagrange density, and this is the Hamiltonian density. So this is the energy density, and this is the pressure density, or the pressure, I guess. And the ratio of the two gives you this W. And and lambda experimentally has W equal to -1. And so you see what can happen here is if this is entirely potential energy, then this W goes to -1, and that gives you the properties of dark energy, and that's explained here. That a mass density that behaves like a cosmological constant is one that's independent of the scale factor, and that's W is -1. By the way, if you work through this part here, what you see is that, well, there's a conservation equation that rho dot +3, the A is the scale factor, that this is the thing that's been expanding from something super microscopic to unity in the astronomer lingo or the astronomer's convention. The astronomers set the present value of the scale factor equal to unity. So then in the past, around the time of the Big Bang, A had to be absolutely microscopic. In any event, this expression here is a constant that represents conservation of energy. And one then finds that the energy density varies with the scale factor like this. And so if W is -1, then the energy density isn't changing at all as the universe expands. And that's the idea of dark energy. And that also is why it is that dark energy is important now, but wasn't important in the early universe, because it presently has a certain value, and it had that same value when the universe was very young and far more dense and hot than now. In fact, incredibly hotter and denser. And so an energy density that we now have only just discovered would have been was totally insignificant for the first, I don't know, year or the first 1,000 years, depending on the precision that you're talking about. So there are various specific models. As I said, this wiki page on quintessence, you just Google quintessence wiki and add the word cosmology to make sure you don't get a perfume. You can then learn a lot. A lot of the basic things are on this web page here. But the bottom line is we don't know what it is. And by the way, if you click on these DOIs, digital something or other. Anyway, you click on the DOIs, you should get a copy of the paper. I downloaded the first 3 on this afternoon. I tell you what, why don't you do this? Why don't you on your computer bring up this web page and then click on the DOI here and see if you can download it. If you can't, then I'll send you the PDFs. Meanwhile, I'm going to make a cup of coffee.
Okay. Wikipedia, physics, that's number 2, DOI.
By the way, I'm told that it helps if you have Google Scholar running on your browser. So you just go to Google and type in Google Scholar and have that show up. Then I think that may help you download. Have you been able to download?
So
Huh?
yeah, so I clicked on the link and it brings me to a physical review letters, and I see the abstract, but when I click the PDF, it says I have to sign in.
All right. Well, bring up Google Scholar and then try again.
Okay. And I just type in the name of the paper. Oh, nice. Very nice.
Did that work?
It did actually.
Oh, good.
So I see the first paragraph starts with inflationary cosmology predicts that the universe is spatially flat, and yada yada.
This is for which one?
The cosmological imprint of an energy component with a general equation of state. It's
Oh,
the
right.
DOI,
Yeah,
I
the
think.
Steinhardt one. Yes. Yes. Right. Steinhardt has been one of the leaders in this field. Um, he's also the person behind, or the main person behind the idea of a bouncing universe, that this period of high density and high temperature that we call the Big Bang, that could have been the result of a previous universe collapsing and then bouncing off the high pressure and expanding into our universe.
So I mean, is that still a theory that's taken seriously today?
Oh yeah, it's quite new. And in fact, I invited him to come here and talk, and he accepted. And then the pandemic occurred, and he decided that he wanted to postpone his visit until after COVID subsided.
It might be cooling down here soon.
Yeah, yeah. Um, I'll send him another email and see. We do have 3 openings in April, and the committee is actually desperate to fill those slots. So that would be good. It would be great to hear from Steinhardt on, and you or anybody else listening could ask him about bouncing universes and about quintessence. He may have given up on this idea, or he may think it's still quite real. I don't know. Anyway, once you say that it's actually not a constant, but the result of one or more scalar fields, then of course there are an infinite number of possibilities. And so there have been various papers saying what might be going on. And of course, this particular equation, this equal to exactly -1, well, it doesn't need to be exactly -1 to agree with the astronomical observations, which of course are always subject to a certain amount of uncertainty, experimental observational uncertainty, because telescopes and detectors are only so good. Now, the other possibility is, or before I go to the other possibility, let me just say that dark energy and dark matter kind of go together, because we know that there's matter that's invisible and that we have tried to detect with a gazillion experiments and have never detected. Now, that matter could in some way be the be what's behind dark energy, or let us say something related to, in other words, scalar fields could be responsible for both. Some of them might have, if we look at this equation, some of them might have q dot squared and the spatial derivatives dominant, in which case W would not be -1. Others might have stopped vibrating and q dot equal to 0, and they just have a potential energy. And then also the potential energy of some of these scalar fields might be huge, others tiny. And so for the same value of q dot squared, some of them would look like dark matter, some would look like dark energy. So the dark energy and dark matter kind of go together if you take this point of view, and that may well be correct. There's also another way of thinking about dark energy, and that's related to some problems in quantum field theory that have been around for 90 years or so. In fact, probably a little more than 90 years. Quantum mechanics was invented in the mid-20s of the last century, and within 5 or 10 years, people had developed quantum field theory, and then had developed it more and more, and then it found that there were infinities. And so by the time there were the 1940s and 50s, people knew that, let me explain how these infinities come about. The deal is that you have to do perturbation theory because these are complicated, these are nonlinear equations with infinitely many degrees of freedom. So you can't solve them in general. And so you need to do, of course, what we do in physics is perturbation theory. We assume there are no interactions at all, and the fields are free, they don't interact, and all the cross sections are 0. And then we imagine that the coupling constant is very small, and so we say that instead of no scattering, there's minimal scattering, and that's perturbation theory. And well, if you work that out and you choose the right theories, you get the right answer in approximately well, for the electromagnetic and the weak interactions, you get the right answer approximately in first order perturbation theory. But when you try to go to second order perturbation theory, you have these loop corrections that are infinite and in general. And well, some of them are finite, but many of them are infinite. And Feynman and Schwinger and Tominaga realized that they could avoid these, they could cancel these infinities if they assumed that the original parameters in the Lagrangian, or the action of the theory, that some of those parameters were infinite. And so then what they did was they just canceled the infinite parameter with the infinite loop integral, and canceled the infinite parts, kept the finite part, and set the finite part equal to whatever they needed experimentally for one process, and then were able to compute other processes correctly. And so they all shared a Nobel Prize for that, which was, I think it was 1960, probably the 1963 or 1964 Nobel Prize. It was announced in 63 and awarded in 64, I think. I was actually taking a course from Schwinger when this was announced. And so we all students, as students, we all clapped for him. He was, by the way, a marvelous lecturer, absolutely extraordinary. it was like listening to God, or what I imagine if there were a God, God would sound like. Anyway, what was I going to say? So the deal is that that if you try to compute, let me see if I have this here. Well, this is a little too, let me get a different one here. All right, this one. And so here are some notes of mine on quantum field theory, and let's see, maybe I should actually teach you some quantum field theory so that you know what's going on here. So basically, we have states, and this is Weinberg's approach, and it's rather complicated. But basically, what you have in all of them is you have an annihilation operators and creation operators, and then you have some vacuum state, and the creation operator acting on the vacuum state gives you a state representing a single particle of given momentum and spin. And that's how you build up the vector space. And then the fields, Weinberg his approach is marvelous, but on the other hand, it's a lot to take if you're seeing this for the first time. So let me try to get you to. All right, so for the spin zero fields, in fact, that's what we're talking about, scalar fields to begin with. You have these, these are called spin zero spinners. So this is sort of a spinless spinner. And it's just it's a normalization factor, 1 over the square root of the energy. And so then you have the annihilating part of the field, a creating part of the field, and the field itself is the sum of the 2 of these. And so this is what the scalar field looks like. It's an integral over all momenta. There's only one spin. You divide by the square root of the energy. Then you have an annihilation operator, standard phase factor, creation operator, standard phase factor. By the way, this P dot X turns out to be the action, actually. If you work out momentum dotted into space minus energy times time, you can see that that's actually the classical action of a point particle of a given mass and velocity moving. Anyway, for a free field, it satisfies this Clown-Gordon equation. And then we get to this 0-point energy problem. So the energy is then this expression here. Let me add an extra space here. So the energy is a big 1/2 out in front, but it's phi dot squared plus the spatial gradient squared plus mass squared, phi squared. And so this is the thing that's this phi dot squared plus phi squared. This is the potential energy of the scalar field. And so this is the thing that, let me see if I can get back to yeah. So this is this denominator, the energy density, time derivative plus potential energy. This is the potential energy, this is the time derivative. And these guys just ignored the spatial derivatives. And the reason they did that is that if all the spatial derivatives do is make the energy density higher. And if you're talking about the vacuum, presumably you have as low a value of this positive term as possible. Anyway, if you take this expression for the scalar field, and you also take this commutation relation that it's, well, S and T are both zero. So it's just a commutator of A of P with a dagger of Q is a three-dimensional delta function of the momenta. If you consider that to be your commutation relation, and this works well in perturbation theory. And so it's basically, it's true as far as it goes. And you then take you expand the field, you expand the Hamiltonian as two integrals over momenta. In terms of these annihilation creation operators, you get a term, you get an expression in which the first term is perfectly reasonable. It's the energy of for each momentum. You integrate over all momenta, and this A dagger A term just tells you the number of particles of momentum P. So this term is exactly what you want. This term isn't, because you then get a delta function of zero. And a delta function of zero, you know, a delta function is, can be written as a Fourier transform. And when in other words, delta, how did I get to this? This is, all right, let me see if I can, okay. All right, and let me also make this visible, so there. So, actually now I've forgotten what I was going to say. Yeah, okay, so the idea here is that this A of P, a dagger of, let us say, K, is delta cubed of P minus K. And now delta cubed of P minus K is an integral d cubed x over 2 pi cubed of e to the I P minus K dotted into x. These are just three vectors. But now, if we go to this point where, you see, when we evaluate this, we wind up with A of P with a dagger of P. So this is A of P, a dagger of P. And that then is an integral d cubed x over 2 pi cubed. And so this is just the volume of space-time divided by 2 pi cubed. And so I guess now that I think about it, you know, maybe one way of dealing with these infinities is to say that space is finite and this integral is actually a finite integral. Then, of course, we don't have delta cubed of P minus K, we have something else. And I've been thinking about things like this for the last, well, for a long time, actually. I've been worried about these various infinities since I've never liked the idea of canceling them. And anyway, so I've been worried about them for, well, since 1963, to tell you the truth, which is when I first learned about them. And so that's this term here, V over 2 pi cubed. And well, V, this just means that this is an energy density, but then the energy density is what? It's in other words, this is the volume of space-time. So if you divide by that, I'm sorry, volume of space. So if you divide by that, you get then an energy density. And that's the factor here, which is a half 1 over 2 times 2 pi cubed, that's 16 pi cubed. Then an integral d cubed P of P0, and that's a terribly infinite expression. It's, I mean, the integral up to some enormous value, big P, whoops, something went wrong here. Okay, let's see, I will. So d cubed p, and it's p0, so a p squared, well, d cubed p, and it's p0, which is square root of p squared plus m squared. But d cubed p is, of course, 4 pi integral dp p squared square root of p squared plus m squared. And so this is, if we ignore the m squared, then it's an integral up to p of dp p cubed. And so that's 4 pi times big P to the 4th over 4. But big P is really infinite. And so we have a quartically divergent quartically divergent energy, whereas the actual value of dark energy is considerably smaller than that. I don't remember what the number is. Let me grab it for you from the web or somewhere. If I could type better, value of dark energy density. So it's 3 grams per cubic centimeter is one way of thinking about it. The way in which it's normally written is differently. So let me write down the actual value according to this thing here. It's so it's equal to 9.47 times 10 to the minus 27 kilograms per meter cubed. No, that's the critical density, damn it. We want the dark energy density. Why do they have a page on dark energy density without saying what the estimated value is? All right, this is a stupid here. Let's just go to Wiki. We're much better off with Wiki. Okay, it's so let's get out the eraser here. And so the Wiki value is around 7, 10 to the minus 30. And that's grams. So I now have to, and it's per centimeter cubed. So I think that would be, wouldn't that be 7, 10 to the minus 27? If we go to meters cubed, we'd multiply by 1,000,000. And all right, so this is 7 times 10 to the minus 27 kilograms per meter cubed. Okay, but that again is not the standard way of writing it. Yeah, here, 10 to the minus 27. Actually, if there's a 7, and then it's 10 to the minus 26. But the way it's normally written here is this. So it's also, here's a way it's often written as. So let me, 2 times 10 to the minus 3 EV to the 4th power. So this way of writing things is units where we have H bar equal to C equal to 1. So when you go to those units, then this energy density corresponds to 10 to the minus 3 EV raised to the 4th power. Now this is something that's 10 to the minus 3 EV is something that is imagined to be a neutrino mass. Now, of course, we don't actually know what the neutrino masses are. What we know about the neutrino masses is all we know is that m squared for one type of neutrino minus m squared of another type of neutrino equals something, and m squared of nu2 minus m squared nu3 is equal to something else. We know these two numbers, and they are sort of consistent with masses of this. They're consistent with masses of that size. And I would imagine that in the next several years, we'll actually know what the neutrino masses are. But when Bill Clinton canceled the SSC, that basically killed experimental particle physics in the United States and effectively the world, because the Europeans then built a machine, the LHC, which wasn't nearly as good as the SSC. And so anyway, but presumably we'll measure these things in the next 10 years or so. Anyhow, the problem is you get an infinity here. And so how does one deal with that? Nobody really knows. There is one rather nice possible explanation, and it was due to Witten a long time ago. And he pointed out that exact supersymmetry, which is abbreviated as SUSY, implies that the energy of the vacuum is identically zero. Well, that caused a lot of excitement back then when one wasn't sure. One thought, well, almost everybody thought that supersymmetry was for sure. By the way, Witten was one of our recent colloquium speakers here via Zoom. When Witten said this back about 40 years ago, everybody thought, not everybody, but a lot of people thought that supersymmetry was a symmetry of nature, and that it would be discovered at the SSC or the Large Hadron Collider, and that, in fact, the Large Hadron Collider wasn't even in anybody's vocabulary because the SSC was the project that everybody was betting on until about 1995 or so, when Clinton canceled it after it was almost constructed in Texas. Anyway, the people thought that supersymmetry would be discovered at the SSC, and then when they built the LHC, they thought it would be discovered at the LHC. Well, there's no sign of it at the LHC, and there's no sign of it in any current experiment. And so one doesn't know whether supersymmetry exists at all. It may exist at very, very high energies. And I suppose that one can imagine that if it exists, if supersymmetry is exact at very high energies, then somehow there's some way to resurrect this even at low energies. And that's the explanation of dark energy. So that's a very nice explanation. Although it's, again, the way Witten formulated it wasn't a cancellation. He derived it from the exact algebra of supersymmetry, which made it a very nice derivation at paper and something quite plausible and respectable, as opposed to just a cancellation. Anyway, it's basically one of the real problems of quantum field theory and current day physics is what do we do with these infinities? Oh my goodness, I've been trying to show you these things and whoops, how did I, can I undo what I just did? Well, anyway, so supersymmetry may exist at high energies, and let me just, in case you didn't see what was on the slides. So one way of coping with all these infinities is called string theory, in which Witten is one of the founders, one of the main people. But there's no experimental evidence really for string theory either. The nice thing, though, is that it takes as the fundamental objects not particles, but instead strings and higher dimensional objects. And so you don't have this problem of having a commutation relation. For example, the equal time commutation relation for a field and its time derivative is I delta cubed of now x minus y, where these are the spatial components. And so you don't have, you avoid this. So maybe I should switch to red. You avoid this thing. So string theory avoids this commutation relation, as well as all of these problems. But again, string theory is something that's unsupported by experiment so far. So these are very open questions. And one advantage of being a young physicist is that you've got these two enormous mysteries that are really quite remarkable. So one really has something to think about. Whereas when I was young, the mystery was, well, why do the particles have the masses they do, and what's going to be the next particle discovered at the whatever was the biggest accelerator at the time, and so forth. What we've got now are these two enormous mysteries of invisible matter called dark matter, and an unknown but extraordinarily important energy called dark energy. And you know, if you do the energy balance cosmologically of the universe, you've got most of it is dark energy, and then this much is dark matter, and the stuff we know about is just this little sliver here. And so we're living in a very mysterious universe. And so these are more interesting and profound and overwhelming mysteries. And so it's great to be a young physicist. I wish you a lot of luck. All right, well, we're way over time. So I'm going to stop now. Do you have a question that I somehow prevented you from answering by talking too much?
No.
Okay. All right. So I'll quit, and I'll put this on the web and send you a link.